incredible as always. Now we get to hear from Bobby Van Ness. He is an alumni from Team 20 and also a past mentor. And last season, he was with the Titanium Tomahawks in Connecticut. And now he's down with us in sunny Southern California. And he will be giving a talk right now on designing your robot around proper forces and loads. Please give a warm welcome to Bobby. And as always, feel free to ask questions in Twitch and in Discord, and we will get to them at the end of the talk. So take it away, Bobby.
All right, let's see if I can get my video going here. All right, thanks for that introduction, Psych. This is a talk that I've actually looked forward to giving for a while. And I think my career experience and experience in FRC lends itself to talking about the structures and the design of FRC robots. So glad I've got the opportunity to talk to you guys about this. I'll go ahead and share my screen. All right, can you guys see?
Yes, we can.
All right, cool. All right, so a quick word about myself. I did my associate's degree from Hudson Valley Community College. In high school, I went to Shenandoah High School in upstate New York. I'll talk about that first experience in a minute, but I guess I'll start. I did engineering science there. It's a 2-year degree. I worked at a local machine shop while I was there. I used my FRC connections to actually get an internship, engineering internship, my first one. During that time, I mentored Team 20, the Rocketeers. I was the drive team coach. I didn't actually coach the drive team, but I coached the drive coach and the drivers, and ran practices, and did a lot of stuff with Team 20. While I was at, I just wanted to put a quick plug in here for community college. It's a really great option to do. It saved me a lot of money in tuition, and I actually was able to do RPI clubs and some activities there while I was going to Hudson Valley. 2 years into my education, I transferred to finish my bachelor's degree in mechanical engineering at Rensselaer Polytechnic Institute in Troy, New York. During that time, I continued to mentor Team 20, basically full bore, and I probably should have tapered off a little bit. I do recommend taking some time in college to go and find the things you like to do. I liked playing ultimate frisbee. I played on a D3 frisbee team when I was at RPI. I got into some combat robotics stuff, mostly 3D printed plastic robots. And I just advocate strongly for doing things other than first in college. First is great, and I don't regret the time that I put into it. But you only go through college one time, and you've got the rest of your 20s to be a young mentor, and the rest of your adult career to be a first robotics mentor. So don't force it in there. Up in the right corner, a cool thing we did in college. That's my capstone project. We designed a lander for Phobos, which is one of the moons orbiting Mars. It was a really cool project, and it was sort of like FRC in that you've only got a pretty short period of time to develop the spacecraft. We had to do all the different components of it, and essentially submit it as a proposal for one of the Mars missions proposals that NASA puts out. So, I'll talk about my career experience a little bit. One of the highlights of my career, actually, I got to work at the NASA Jet Propulsion Laboratory for a 6-month co-op. Again, this was I really attribute my luck of getting to this point, a lot of it to First Robotics and the experience and networking connections I got as going through the program. I actually worked in Mark Rover's old group, so he was long gone at that point, but it was fun to see his name in a couple of old documents and things that I was referencing. When I was there, I got to develop a patent pending nanoparticle detection method. And among other things, the other things I got to do was a concept for an internal transfer mechanism, robotic assembly. Did some early dynamic calculations for the capture containment return system. And I developed the latch, which is, I guess, the final latch that goes between the lid of the orbital sample and the samples themselves. If you see this picture down here, that's one of the Mars rock samples. So the rest of the assembly, rest of the mission collects the rocks, drills out some cores, puts them into these titanium tubes, caps them off, and puts them in the orbital sample. And I developed the latches for those. So what I'm doing now, well, before working where I currently am, I worked at Pratt & Whitney, which is an aircraft engine company in Hartford, Connecticut. during that was the time when I mentored Team 2170, and I did some pretty in-depth structural analysis on components in the engine. I was working on the high pressure turbine first stage. This is what those blades look like. I was doing a lot of structural analysis, so I was creating meshes, applying loads, getting stresses back, and running pretty detailed lifing calculations to figure out how many cycles that those blades were going to be able to withstand, how many flight cycles in the engine, and keeping those within safe limits, and tracking down other chemical properties like stress corrosion cracking and some very nuanced things. But I can tell you they do great work there, and it's a really good company. But earlier this year, it's time for a change for me, so I actually took a position at Honeybee Robotics here in Pasadena, California. This has really been an awesome job for me. It's pretty much the closest career equivalent to First Robotics that I've found through all the places that I've worked at. So I've really enjoyed that so far. If you look here, the couple of the things, this is the Trident drill, which is actually it's some of it's based on Apollo technology, but it's a really cool thing that's being sent to a couple of different locations for different missions. There's adaptations of that are still getting used in new designs. Um, I don't have any of the current things I'm working on because they're not out yet, but when they come out, I hope to update this presentation with those. So, First Robotics. All right, I guess I didn't fully finish this slide. I started out in Team 20, the Rocketeers, as a student. I was the co-captain, driver, mechanical designer, all the things. Um, I've done 6 seasons of mentoring since then. I've mentored teams 20, 68, 44, and 2170. And now I'm a free agent in SoCal. So if you're on a team in the area and you're looking for another mechanical mentor, there's a whole lot of us out there, but I'm a free agent. So, all right. So this course is going to go over some of the basic physics. I'm going to talk about two separate things and split this presentation up basically into handling loads and the structural design of your robot, and then dealing with the forces and moving things, the heavy lifting. How do you get your motors to properly lift things quickly and efficiently? And then I'll open it up for questions at the end. So the first thing is really how to define forces versus loads. So a force will act on a structure, and in acting on that structure, it creates a load, and that load has to be dealt with structurally with the components. And the structure, when I say that, that's basically anything that's dealing with loads. So in this case, the hook is structure. The cable that comes down from that hook into the winch, that's all structure. All the stuff at the bottom, the winch assembly where it's bolted to the superstructure, those are all things that are handling loads. And so we want to make sure that all of those are up for the task. They're not going to break. So that's the failure prevention perspective here. Um, the other side of it is we want the moving parts, all the things that are dealing with energy, to be able to properly transfer energy into the robot and perform the tasks that we want them to perform. Um, I've seen a lot of times where load calculations are not done either through the gearboxes or the motors, and things will go to competition that just aren't up for the task, and you see motors burn out, you see gears break or arms, crumple, fold, break. I hate to see that because um, the you can design your robot, you can do these calculations up front to prevent those failures, especially at competition. And it doesn't take a whole lot of time. It just takes a little bit of know-how, and you can get it down to a point where it's mostly intuitive, and you can design your robot to hold up to those tasks. So forces, they create loads on a structure. They can be created by gravity, inertia, springs, actuators, any of the moving things. Um, and we need to size our motors, springs, actuators, whatever assemblies that are handling forces appropriately uh, to not burn out, to complete the tasks, and to do it quickly. Loads created by forces, we get stresses from loads. So loads will impart a stress on a structure. We want to understand those stresses and design the structure to be able to hold up to them. So the structure, as I said before, any load-bearing object in FRC, the chassis, superstructure, wheels, arms, whatever, anything that can break basically is going to go into that structure camp. And the goal is to design a robot that can reliably handle a season of beating on the field. That robot's going to get trashed. Just like 2016, I think there not many teams that didn't have some sort of break or some sort of, something that failed. But if you size your components correctly and you put things in the right places, triangles are strong, prevent racking, prevent parallelogramming, you can give yourself the best chance of getting through a season without a major structural failure. So the first thing we're going to talk about, so this may be really starting from the ground. This is a big chunk of mechanical engineering. This is a lot of your first 2 years of college. They're going to talk about how to handle stress, how to deal with all these different types of stresses and go through these in-depth calculations. I'm not going to try to cram in an entire first 2 years of a mechanical engineering undergrad study. I started to, and I had to sort of pull myself back. There's so much to get into here, and I'm trying to just give you guys a sort of an intuitive understanding. I'll give a couple examples here. So the courses that would see these sorts of things like intro to statics, mechanics of materials, intro to engineering, elements of machine design, like those are common undergraduate courses that you'd see in a typical mechanical engineering degree. So the most basic formula, and you would probably see this in high school and go even a bit further, but stress equals force divided by area. So our stresses are it's really like a pressure almost. And there are different types of stresses. We've got compression, tension, and shear. Those are your three primary stresses. So what do those look like? Compression, all right, well, you're squeezing this blue box here and it's bowing out. It's because it's in compression. Tension would be like a cable or a line or something that's getting pulled apart. It's trying to pull, elongate it. And then shear is sort of a side load that isn't quite compression or tension, and it's if you think like it's moving plates of a material like sort of in parallel. And if you combine some of those three forces, the three types of stress, you can get either bending or torsion. And these are some common failures. Tension, bending, and torsion are really going to be your most common failure modes in first robotics. So yeah, just bending and torsion are combinations of the three primary stresses that we talked about a second ago. So every material that we look at is going to have a certain stress that it can handle. That's the material strength. A few forms of those, we've got the yield strength, which is the maximum amount of stress a material can take before it starts to permanently deform. And if you look at a tensile test, you get necking, you get the material like just elongating and then not coming back. There's a certain amount of deformation a material can take called elastic deformation, where it'll actually return to where it was. It'll go back to exactly the way it was before. But if you exceed that limit, you start to permanently deform the material. And you can do that sometimes quite a bit with some materials before you ultimately fracture it. So that's why you'll see there's yield strength. And then if you go up a little bit more, there's ultimate strength. And then another important one here, I'll talk about it in a second, is this line here. That slope is equal to the elastic modulus. So that's basically the stiffness of your structure. This is a lot to take in. So if it's not all sticking, that's all right. It's really just sort of, I'm trying to just get you guys to understand this intuitively. So again, yeah, the modulus of elasticity, or Young's modulus, defines the stiffness of this material. So an example of what tension looks like here. So if you think of like a wrecking ball, it's got this line going to it, and that line would be in tension. So we've got this center of mass here, and then it's pulling on this cable. That cable is going to have a certain stress on it, and that's based on the cross-sectional area of the cable. So bending. So bending is caused by a load that's perpendicular to the base. The bending stresses, they're going to rapidly increase as you increase the distance from the base that you're applying it. If you think of like a robot arm or something, it's going to take some load on the end of it. The distribution of that load, go back, is going to look like, if you can see that this FEA picture down here, where you've got this, you've got tension on one side and compression on the other, and the stresses are highest at the base. So that's why if you see like a piece of metal or something fractures at the base where you've got it mounted to a stiff surface. That's why. It's because the stresses are highest at the base. There's another important thing here called the moment of inertia, and that describes the stiffness of this particular object in bending. So the higher your moment of inertia, the lower your stresses are going to be, because you're spreading out where that force is dealt with at the base. So you can also see sometimes there'll be like a triangle that has a higher cross section, a higher moment of inertia at the base, and that's because the stresses get higher as you get towards the base. And then so that bending stress is defined as this equation: moment times the y distance, which would be the distance on that cross sectional area, divided by the moment of inertia. So how do we use this? So we're going to jump back and use that hook from the previous example. So this hook is under a couple of loads here. We've got tension and bending, and I think I left out tension in this example. So you would have to actually include the tension stress in this as well, but it would be quite a bit lower than the bending stress. So just to preface this, I did leave out the tension, so this is just the bending stress. So let's set some arbitrary dimensions for this hook. Let's say we've got a 1-inch thickness, and we've got, or excuse me, 0.1 inch material thickness and a 1-inch height. So we're going to apply a load, 150 pounds of robot, and that includes the robot, the battery, and the bumpers. 150 pounds is usually sort of middle of that's about upper range of what a robot's going to weigh. Let's arbitrarily say that our distance from the force to our cross section that's in bending is 1.5 inches. And then let's calculate our moment of inertia. So the moment of inertia can be calculated by 1/12 base times height cubed, and that's for a rectangle. I think I had it on the previous slide. There's a number of different types of moment of inertia calculations, and then there's the parallel axis theorem, which I don't have time to get into in this presentation. That's usually the first few lectures of a college course in that sort of in statics or stresses like that. So a lot of this, like I said, is first, second year college stuff, and it takes some time to get through. So we've got a moment that we're going to be dealing with, which would be the weight of the robot times the distance from our bending cross section, and we've got this moment of inertia that I've calculated here. And we're going to take this bending stress. Remember, we've got two of these hooks. You can see this here, two of these hooks that are supporting that load. So I'm going to multiply that moment of inertia by 2. And using this 150 pounds of robot at this location, 1.5 inches from our cross section, we can calculate that we're going to see 47 megapascals of stress. So what do we do with that? Well, I think I had previously a material chart here, and we've got 47 megapascals, and let's say we've just designed it out of aluminum, right? Well, okay, aluminum's yield strength is 276 megapascals, and that's something we can look at. We can say, hey, we're pretty comfortable with the stress range. We've got maybe a 5x margin on yield. Really, you want to make sure you've got at least like a 2x margin on yield on pretty much any FRC application. That's kind of the minimum that I usually feel comfortable putting a robot through as far as stress. So let's look at another example. A common feature on a lot of robots in 2019 was the buddy climb. So with this buddy climb, let's just say we're going to use a 1-inch box tubing. And in all disclosure, I actually did not design any buddy climbs in 2019, so this is really a lot of speculation here. But we're going to look at the sort of simplify the robot problem into these beautiful little robot clip art pictures that I made. And we're going to say, we're going to look at the particular area and load, and we're going to approximate it a lot because there's a lot more bends and things going on this robot right here. We're going to simplify it and just say that it's just a piece of box tubing coming out. Let's say it's 20 inches to our maximum force location, and we're going to apply our 150-pound robot load right in the end of that. So That's 20 inches out, 150 pounds of robot. We can calculate our moment of inertia uh, with that same square, the 1/12 base times height cubed, and we can get this number, which actually is a little bit more complicated with that than that. If you're dealing with a box tubing section, you're essentially subtracting out the negative area in here. Um, and so let's say it's got 16th wall thickness, which is 0.0625 inches, 20 inches out. We've got 3,000 inch-pounds of moment that we need to react. So take that 3,000 inch-pounds. We've got our y distance, which is half the distance of the cross section, which is half of an inch. And we're in the highest stress is going to, if you look at that, the FEA that I showed, highest stress is going to be at the edges here. So that's why I'm taking that y distance. Y distance is basically the distance from the neutral axis, and that's half an inch here. So we've got two bars that are holding up this robot. So we can multiply again our moment of inertia by 2, and what we get out of this is 21.8 ksi. Um, that's that's 150 megapascals. And if you remember before, aluminum was about 270 megapascals to yield. So if you were to put a factor of safety of 2 on that, we've then got 300 megapascals, which is over the yield strength of aluminum. Now, this is the sort of thing where it might work. It would be certainly leaving yourself open for potential failure. And this is something that I mean, if I were on a team and we were planning to use 16th box tubing for this particular application, I would probably start making some noise and saying, hey, this is really not adequate. I'm not comfortable with operating this close to the yield limit of the material, because we're going to have other deflections going on here. And when this robot bounces, if it's not going to be perfectly stable. So you're going to see some high loads. You're going to see some maybe all the way up to 300-400 megapascals, or if it snags or a robot jostles or falls or something, you don't want to be operating that close to your material limit. So we've got this number. What do we do with it? Well, we can increase the wall thickness to 1/8 inch, and then that's going to essentially cut our stress down in half, because it's going to approximately double the moment of inertia. But what that's going to do also, it's going to make it twice as heavy. So we don't want this thing to be a really heavy run of material. So how do we use our material more efficiently? Maybe we look at 2x1 box tubing instead of 1x1. And if you could fit that under a robot, I mean, of course, you get into some areas where now maybe the robot can't fit onto it. It's sort of a battle between performance and between the structural aspect and making it as light as possible. So um, if we could fit that 2x1 box tubing in there, maybe we use that instead. Or maybe we go with 1/8 inch wall thickness and we pocket out the sides of it where the sides don't see quite as much stress, and leave the top and bottom stiff so that they can support the bending load of this. So there are some options. If you really just want to get to this number and understand what your stresses look like, that's one of the most important things, is to know um, where you're at in terms of material limits, and just make sure that you're not getting close to exceeding the yield strength, or if it's something that's going to be undergoing frequent loads. This is something that would only be used, once per match. It's not going up and down 20 times a match and getting those high stress cycles on it. So once a match, you certainly want to be clear of yield, but maybe you don't need to keep it clear of the endurance limit or other material properties that pertain to cycling loads. There is such a thing as a fatigue damage, which if you operate in let's say even like 70 or 80 megapascals, like you're well clear of the material limit, you might see that there's a failure at some point through the season if you're getting a lot of cycles on that particular material. So some things to avoid, and some more lovely clip art here for you guys. I've seen racking happen a lot with superstructures and elevators. And if you can imagine, this is like a sort of a generic structure for an elevator. And you get a side load at the top, either through gravity or through whatever you're lifting, or another robot hits you or something. And then the whole frame racks over like this. And some people say, we call it parallelogramming. Um, that creates extremely high stress points at your corners. And it's really just not a good thing for performance, for structure, for anything. You really want a stiff structure that doesn't deflect a whole lot. Because if you think about this, I actually didn't mention deflection here, but you could think if you were to get some deflection on this arm, you might run into a situation where you're sort of dumping the robot off the back end, and you definitely don't want to do that. So uh, this can happen in a lot of different types of structures. So what do? You put in some triangles, some cross beams, cross sections, and maybe they don't need to be as dramatic and pronounced as this. Maybe it's just your gussets are thick, but you definitely do want to be dealing with those loads in a deterministic way. So another one, so buckling, uh, I guess not super common in FRC, but if you had a really thin tube that was pretty long, you might actually see uh, well below of the bearing strength of that beam, it might flex out, buckle, or break in some way. So other things are stress concentrations. I'd see a lot of stress concentrations that lead to sort of puzzling failures. Um, some of it will come from pocketing on gearboxes or just pocketing that doesn't understand grooves and things that are directly in the load path. So if you're going to do snap ring grooves, that's a big one I've seen. If you're going to put a snap ring groove in a gearbox or on your drive output, don't put it in the main load path. So if we've got this sort of top-down view on a generic like West Coast drive orientation, you've got your sprocket here, and that's getting power input from a chain or a belt, and you've got a clearance gap to the frame, and another maybe clearance gap to the wheel, and then the wheel gets driven. So your primary load path in this situation would be from the wheel through the shaft to the sprocket. I've seen before where teams will put snap rings on that shaft. And a snap ring, if you look at this, so this is sort of just what a stress concentration looks like at the base when you've got a hard angle like that. You get really high stresses, much higher than the entire stress, like much higher than what that shaft is dealing with. So as you go across a shoulder or something like that, you get, it can be as much as 5, 10 times the stress. There's calculations you can do, and there are, again, there's I'm sure an entire course in mechanical engineering on just stress concentrations. I know I've dealt with books that just go through pages and pages of different orientations of stress concentrations. Um, but really just understand, like if you put a snap ring groove in here in this wheel, it's seeing a lot of cyclic loading. Or if you do something like this in a flywheel, right? If you have a flywheel that's going really fast and it's taking shock loading, you put a snap ring groove in there, you might actually see a failure at that snap ring groove. That's going to be the most likely place to fail because it's got such high stress concentrations. It's going to be the first place to open up a crack, and that crack's going to propagate through the rest of the shaft. So really just keep your snap rings out of the load path. Um, keep your stress concentrations as much out of the load path as you can. That means rounded edges. That means polishing things, making sure high stress locations are smooth. Um, and I wish I had some more images here, but it's something that you'll see a lot in the industry as well, and just mechanical engineering is dealing with stress concentrations. So this is another one I want to talk about, and I didn't want to single out any teams, so I took off the team number down there. But it's a pretty awesome robot. I do love this robot, and it was really killer this year. But there's one thing on it that just made me a little bit uneasy, and that would be the flywheel. So I've seen a couple of teams this year put flywheels on their robots that are really large, really high energy storage, and they're spinning sometimes significantly faster than the flywheel that's actually interacting with the game piece. Now, from a performance perspective, that's awesome. You can store all the energy you need, get a wicked fast shot rate, and it can perform really really well with that. However, we've got a flywheel disc here in the, let's say, 8-inch diameter, and it's spinning at 20,000 RPM. Well, I was working at Pratt& Whitney on aircraft engines around the time when these robots started coming out. And the things that I was analyzing on my screen were not all that much lower or higher in energy than these FRC robots. And we were doing tons and tons of structural calculations to make sure that these were safe to fly in a customer aircraft, to make sure that they're not going to ever crack or come apart. And so this is just a case where, I mean, it's not, I wouldn't worry about this particular team, but I worry about the team that copies this team and puts it on a hex shaft or 3D printed, PLA hub or something. Um, so really, you should understand there's a lot of stress on here. And I think when I did a generic calculation on it, it was something in the neighborhood of 200,000 pounds that were radially pulling outwards. So you could think if you were to propagate a crack, it could chuck a pretty dangerous chunk of material out. So really, just this is one of those cases where you have to understand what your loads are doing, because if that were to fracture at full speed, let's say 15, 20,000 RPM, there really is no FRC field or mechanism that can contain that. So it's a safety thing, and I think somebody really ought to understand the loads going through your robot if you're doing really high energy things like that. Similar things like that would be the catapults in 2014, these enormous springs that we had on our robot. We did a lot of analysis to make sure that we weren't exceeding the stress limits on these. But even at one point in our 2014 season, we had our catapult shear in half. And just thinking about it afterwards, like if that were to let go, it's just so much energy we're dealing with. And that's why it can be really important to safety wire things to make sure things aren't going to let go and become uncontained. So yeah, sort of why is this important? It relates directly to robot reliability. Um, you can get structural damage during the season, which is almost impossible to fix sometimes. Could mean you need to weld and fix things. Maybe this year, the future seasons without the bag, that might be a little bit more easy to fix. Um, but I've certainly seen robot structures fail to a point where they've got to sort of rig together some scrap pieces of metal, and it's never really the same after that. So if you design it up front for your robot to handle those loads, and your structure is up to the task, it can make for a much more reliable robot. So finite element analysis, I get asked about this every now and then, and I think it's a really good visual tool. I think it's a great tool to understand what your stress contours look like in a given part, but it's only really useful in a few limited FRC applications. Um, this actually is a example that I put together for an interview for one of the companies I was looking at. And it just sort of explains the process of finite element modeling. So you create your CAD, you mesh it with a bunch of little triangles here or squares. There's a lot of different types of elements you can use, but if you use some of the simple plugin tools, they're going to just, they call it tet blasting, tetrahedral elements. So they're essentially 4 nodes or 9 node elements that approximate the geometry. Like this is a complex geometry here, and this is a generic blade. It's nothing proprietary or all that interesting, but a generic blade. But it's still a complex geometry. You're not going to find any calculations in a book for how to deal with the stress in this. So that's where this is useful, right? Where you can approximate it with all these little triangles, apply your loads. In this case, we've got a radial, like a centrifugal load on it, which is the dominating force, and then we've got a pressure load on the side. And then in an aircraft engine, a turbine blade like this, you've got all sorts of thermal loads, which I did not include in this quick calculation, but you use that mesh and those loads, and you click go, and it's pretty simple in Autodesk, and you get stress contours. And you can just by looking here, like I can see this, and I can say, oh, my attachment down here has the highest stresses of the part, but then we've got some high stresses in the under platform region. The same way on a first robotics gearbox, you can say, hey, like this bearing interface, maybe the loads are really adding up in this one location. Um, but the thing is with FEA, garbage in, garbage out. If you don't understand the loads that are going through, FEA is not going to solve all of your problems if you don't understand what the problems are. So you really need to understand what your loads are, what it looks like, and then if you've got that down, FEA can be a helpful tool, but it can also be sort of a dangerous tool if you're using it as a patch fix to not understand the core physics. So really, you got to understand your load paths. You got to understand how the stress is flowing through your robot. Pocketing, another thing I hear about a lot, and I just stole this off of Google from Sam Cruel. I don't know how to say that, but so you want to understand your load paths, and this one did a pretty good job of it. If you look at the bolt holes, they're pretty close to where the bearings are. Um, there's going to be loads between bearings, like when you've got gears interacting with each other, there's going to be pushing and shear loads between the two of those. So you want to make sure that there's material there. Looks like this one did a pretty good job of it. Um, and then you're going between the bearing locations here and your mounting points where it mounts to the robot. You want to make sure that there's a lot of good, strong triangles in that area. So I'm not going to go too far into the details of pocketing. That hopefully we'll hear from some other hear about this a little bit more later in the design presentation. So the other half of this presentation, if I've got time for it, is dealing with forces. So you've got to understand the forces through your system if you're going to design proper, climbers and and lifters and other things, the drivetrains, elevators, flywheels, those are all things that need to deal with forces. You've got motors that need to put out a certain amount of torque, power, and we're going to talk about that. So the basic physics here, force equals mass times acceleration. If you've taken a basic physics class, you know exactly what that means. You've got a mass that's going to accelerate proportional to the amount of force you're applying to it. Now, we've got one very common acceleration force, which is gravity. Gravity is one of the main forces we're dealing with in first robotics. We're lifting things up. We're lifting the robot up. And climbers, it's one of the biggest forces and things that we're going to have to deal with. Power. So each motor is going to have a maximum power output. We'll talk about power curves in a second, but that's either force times distance, which is energy. I have that down here. Divided by time. So it's the amount of energy you can put out from your motor in a certain amount of time. So if we're lifting up something, it's how quickly we can counteract the force of gravity over a certain distance at a certain time, or it's torque times velocity if you're talking about rotational stuff. So we've got 5 main forms of energy storage in a first robotics robot. We've got the chemical energy of the battery. We've got mechanical energy either in springs, deflection, and a couple other things. We've got pneumatic energy in our air tanks. We've got kinetic energy in flywheels, so we're transferring momentum and thus transferring energy between flywheels and other moving objects. And then we've got gravitational energy. So we've got things lifted up. Think of like a carriage on an elevator that's going to have some gravitational energy stored there. So the force that a motor provides is called torque. It's a twisting force. I'm sure most of you guys understand a little bit about this at least. So our torque is going to be highest when the motor is at stall, when the motor is given power, but it's not yet moving. And then there's going to be, so if you look at this yellow curve right here, this is the power curve. So this is the RPM on the x-axis and the either power, torque, or amperage on the y-axis. And as we increase in RPM, you can see our torque starts pretty high up here, which I believe is around 1 Newton meter, and comes down linearly as we go up to our maximum RPM. And this is for the Neo 550. So as we go from 0 RPM to 11,000 RPM, our torque will linearly drop. But remember that power equals torque times velocity. So as our torque drops, our velocity increases, which is this RPM down here. So that obviously increases linearly as the x-axis. So you're multiplying torque by your velocity, and you're creating this power curve. This is the amount of power output in the motor. So this is how quickly you can accomplish a task. So if you're designing your mechanism and you want it to do a high power task very quickly, you might want to design it to operate somewhere within this power band. And however, we've got other things to consider, like there's this amperage curve down here. And if you remember from our electrical boards, we've got a maximum power distribution slot breaker of 40 amps. So if you exceed that 40 amps for a duration, 20, 30 seconds or so, usually it'll pop the breaker and it'll shut off that particular mechanism. Or if you exceed 120 amps out of your robot, you can actually shut it down for the match. And I've had that happen before. Usually that's a drivetrain thing, but you don't want that to happen because you're sitting dead for the rest of the match. Whereas if you pop the individual breaker, it will come back as the thermal snap action breaker cools down. So we want to design the reduction for the motor to give us this optimal, give us at least a known power range and known current and amperage output. So I'm going to just sort of gloss over this. The gears give us mechanical advantage. There's other forms of mechanical advantage that linkages and other things that can amplify our force, but I'm going to just focus on gears here. And I got an example coming up in a second, but I'm going to talk about counterbalancing. So we've got this force of gravity that we need to overcome as we go up and down on an elevator. And if you're smart, you can offload most of that gravity force with a counterbalance. And one of the most common ways to do this is with what we've called on certain teams death springs, constant force springs. So you've got to be careful with these because you can lose a finger. They're very, very dangerous and sharp, and they hold a whole lot of energy, but all that energy is awesome for making a robot really high performance. So if sized correctly, a lot of times with an elevator, all you have to deal with your motors is the inertial force. It's like as if it was laid down flat, and you don't have to lift that heavy carriage, which can be 15, 20 pounds. You don't have to lift it up and down each time. Instead, you can just sort of accelerate it, and that spring is taking up most of the gravity. And with these gravity offloads, you usually want to provide slightly less than gravity so you can still have good control with the motors, but you want to make it so that your motors are not using a whole lot of current to hold position. Other forms of counterbalance, linear springs, torsion springs, gas shocks, those are all just different forms of energy storage that are maybe a little bit slower. Gas shocks are damped usually, so they have a certain speed that they put out energy. Um, and then linear springs, torsion springs, those are things that are great for launchers. It's a very quick release of energy, and it's non-linear most of the time. And so those can be good in shooting applications or catapults and those sorts of things. So how do we select a motor that's up to the task? Is it an application that's really power heavy, climbing, stacking, heavy lifting, or something that's going to move very fast, very quickly? Well, then we want a high power, robust motor to do that sort of thing. Does it need to operate continuously? Is it an elevator or arm that's going to have to hold position for the entire match? Well, maybe we don't want to use an air cooled motor at that point. Then we want to use a Neo, a Sim, or I've never actually worked with one, but maybe a Falcon. Um, or if we've got a continuous high RPM like a flywheel. We want maybe an air-cooled motor. The Neo 550 is an outrunner motor, so it's got nice air cooling, and then the Falcon's another good option for that as well. Um, because if you're going to be up to speed for a while, you want to make sure that that motor is cooling itself down as it's drawing power. And a lot of times you'll find that there are other forces on the robot that you didn't anticipate. There might be some binding or some friction that you didn't account for. And so just leave the option open to increase your torque, increase your power, whatever you need to do down the road to be able to make the robot perform the tasks once you're in the testing phase. Note that 20 DP gears, your typical like Vex Pro gears, they're not indestructible. So if you put them on a really high torque arm and that arm slashes around and it hits stuff or whatever, a lot of times you're going to see you might break gear teeth right off of it. And this can happen in drivetrains as well. So uh, you definitely want to understand the loads that are going through it and try to manage it as well as possible. Um, Counterbalancing can lower the amount of load on your mechanisms. And so what we want to do is we want to understand our mechanism, the power flowing through it, and then we want to deliver a very efficiently working robot to our programmers or motion control subteam. So I'm going to give an example of, I think this is 5254's robot. I'm pretty sure I've seen it somewhere before, backslash. Uh, so let's say that we've got an arm length. I'm going to add some arbitrary numbers here. 20 inches arm length, and we got 20 pounds force at the end of it. So let's say a pretty heavy end effector here. What's that mean? We've got 400 inch-pounds of torque that we need to react, and in this case, it's torque, not moment, because it's actually the twisting force that we need to react with energy. So in an arm application like this would be a continuous load. So it's dealing with it for the entirety of the match. So we want to make sure that the arm is up to the task for that. So we don't want the motor to overheat. We don't want it to stall out or anything like that as we're going through the match. So we want to make sure that our amperage is within the continuous amperage limit. And then we also probably have a performance goal in mind. Maybe we want to be able to go from all the way down to all the way up in 1 second. Um, and that means that we need to be able to deal with this 400 inch-pounds of torque and be able to do that 180 degrees in 1 second. So let's move forward with some parameters like those. And remember, we've got this motor curve. So what's it take to get to that performance guideline or performance metric? So from the locked rotor testing from Robotics, let's say we're going to use a Neo 550. It can survive 20 amps continuously for 220 seconds. So that's more than a match. That's about a match length. So we're comfortable with that. So yeah, like I said, you don't want to pop breakers. So let's design to operate at 20 amps continuous when this arm is just chilling out on the side like that at maximum load. And with that, remember that. So torque out is going to be the motor torque times the gear ratio. And at 20 amps, when this blue curve gets down to 20 amps, um, that puts us around 0.25 Newton meters of torque. So torque out equals torque in times gear ratio. Okay, cool. So we determined from that, we've got our torque in of 0.25 Newton meters. Divide that 45.2 by 0.25, and we've got 181 to 1. Now, that's a really high gear ratio. And 5254 probably doesn't want to put that all through versaplanetary, or maybe they do. It's up to them, but it's probably going to break if you put it through a versaplanetary. So what do? You want to put a good amount of that through maybe a two-stage versaplanetary and then a final reduction on the arm. But we'll get to that in one sec. We've got that original performance goal of 180 degrees in in 0. What did I say? 1 second? 1 second. So our motor's at 8,000 RPM when we're in that current range. That's right here on the x-axis. So 8,000 RPM. We've got our gear ratio of 181 to 1. 8,000 RPM, of course, is 8,000 divided by 60 revolutions per second. And we've got half a revolution on the output. So essentially with that gear ratio and operating in that current range, we would go 180 degrees, which is 0.5 revolutions, and 0.68 seconds. So we're in the clear with this gear ratio. That gives us the optimal, it gives us a good continuous current, and it also gives us the performance we want. Actually, it does better than the performance we want. So we're in the clear. And a note on gear ratios, as I was saying, is 5254 wants to put probably another final reduction. Let's say 36 to 10 final sprocket ratio if they were to do a chain drive to the arm, and then 2 7 to 1 versaplanetary stages, and that puts you right around that 180-ish to 1 gear ratio. So I'm going to give another quick example. I know I'm running out of time here, but another common one is climbers. And I've seen this one happen a lot where teams either gear their robot so high up that the climb takes forever to get up, or they undergear it so much. I had a team one time, they geared their climber close to what a flywheel would be geared at. So when that happens, this is usually the cause. It's just there was never a load calculation that was done for that. And so just to rip through this real quick, we've got 150 pounds of robot acting on this hook. We've got a winch and drum assembly down here. So let's say we want to pick this robot up in 2 seconds. We've got a total distance that we need to lift that robot of 30 inches, 150 pounds of force. So combine all those numbers, 30 inches of travel divided by 12 inches per foot times 150 pound force gives us 375 pound-feet of energy that we need to deal with. That's 150 pounds of robot at, what is that, 2.25-ish feet. And so that in metric is 508 joules, which is Newton meters. So we've got a certain power output that a motor can give us, and I'm actually going to, pulling from what we actually did for this this robot, RS775 power is about 350 watts output, and that maximum power output is at about 9,000 RPM. So in a climber application, contrary to an arm, we can be a little bit more comfortable maybe operating towards the peak power of that particular motor, and we can try to complete this climb task as quickly as we actually can. So that means we're going to design our gear ratio to operate somewhere around that 9,000 RPM peak power. And this calculation here is just to make sure that our performance goal can be achieved with this particular motor. So those 508 joules, we're going to be taking care of those in 2 seconds. So remember that power is energy over time. So joules over seconds. We've got 254 watts, and I swear I didn't plan on that to be 254. It just sort of happened. So we've got 254 watts to deal with. We've got 347 watts out of our RS775, so that means that motor should be more than capable of lifting the robot within the amount of time that we want. So some more considerations, as I just mentioned, we're comfortable operating above that 40 amp breaker limit for a short duration, and putting that much current through the motor because we're comfortable that it's only going to happen for the last few seconds of the match. We've got the entire time until the next climb, even in back-to-back matches, for that motor to cool down. And it's the kind of thing, if you climbed early and the motor stuck or something, yes, you might burn it out, but there are some risks you have to take in FRC. And I think climbers are one where you're generally trying to operate as close to your peak power with some amount of margin um, to complete the task as quickly as possible. So we've got that 150 pounds of lifting force. Was I getting at here? Yeah, how to deal with that. So 150 pounds. We've got this drum now, which is a, let's call it a 1 inch radius drum. I don't think I put that in here, but 150 inch pounds is the output torque on that drum required to lift up the robot, which is 17 newton meters. Well, we've got 0.35 newton meters at our maximum, at our peak power for the RS775. So again, the torque out equals the torque in times the gear ratio. And if you just flip it around, do a little simple algebra here, you can get a gear ratio of approximately 49-1 and 2 7-to-1 stages. So 49-1, 50-1-ish, that's a pretty common gear ratio for climbers. If you aren't comfortable doing these calculations, that's sometimes a pretty fair place to start if you've got a small drum. Of course, if your drum's going to be 2 inches in diameter, you're going to need to increase this to 2 times this gear ratio with that particular motor. So then maybe you need 100-1. But it is really useful to just do this calculation and make sure you're in the safe motor operating range ballpark. And so I think that's my last slide, right around 50 minutes. And if any of you guys are still awake, I would love to take some questions.
Thank you, Bobby. That was incredible. Could you please stop sharing your slides so we can see your face for the
Yeah, of
next couple
course.
minutes? So I think we only have time for a couple of questions, but that was a lot of really great information. I know I learned a lot. Some of it was like went over my head, but like a lot of it was really like I'm not a mechanical guy, so you know.
Yeah, well, as I mentioned, I mean, that's like a lot of this is stuff that you're going to see in your first few semesters of mechanical engineering, like undergraduate studies. So I tried to compress a lot of it into here, and I hope at least some of it got through. Um,
I it definitely I think like it's a good thing to like start thinking about like certain just think about it, right? And like try to
right,
like,
yeah,
incorporate it when you design. I think a big question that like some of us were thinking back here was how do you know when to decide what to like to do analysis on a part or when to like hand wave it and just like send it out, right? Because sometimes like it's impossible to do analysis on everything, but like how do you make that distinction?
right. So the things that I sort of just hand wave, and I try to hand wave it at least with like a whiteboard calculation or something. I really hate going in blind with a gear ratio, but the things that I'm comfortable doing that would be like for a roller or like an intake or something. I have some numbers that sort of slosh around in my head, 12-1 on an intake or something like that. And those are things that maybe you need to just try it and see how it reacts. Maybe you need a little bit more torque, a little bit more velocity to overcome jamming or something. So intakes are things that I sort of tuned by performance. Um, but then when you've got something like a climber is like hands down, it's going to be the highest load thing on your robot. And you don't want to go through, burning out motors and breaking things to figure out what your gear ratio is when you can spend 20 minutes on a whiteboard and figure out sort of where you want to operate. It's not too difficult of a calculation to figure out sort of what your torque range is and make sure that you're operating in a sort of a safe location. And
Uh, a- as a really quick last question, this is
yeah,
just from the Twitch chat. This is from Tushko123. And their question is there a benefit to doing your own load calculations, and as you showed, instead of using FEA in a program like SolidWorks? You mentioned that FEA doesn't give you the full picture, but is there anything else?
right. Well, absolutely. I think it's really, really important to understand your own load calculations and where those are coming from. FEA is approximating it with a bunch of little triangles, so it's doing these core calculations for complex geometries. But if you're relying on it, for your core loads, like you've really got to understand your load paths, especially if you're going to do sort of a piece part FEA analysis, right? That's redundant FEA analysis. Uh, if you're going to do like a piece part analysis, you want to understand where the load is going through and what the actual inputs are. That's some of the toughest stuff, right? Is your inputs. It's not very hard to just click a couple of things and run an FEA model, mesh it, and just go with it. But if the loads you're putting in aren't accurate, uh, you're not going to get accurate results. And it can be great for calculating stress concentrations or figuring out where you want to pocket, where you want to remove material from so that you don't overstress things or that you can lighten things as much as possible. And so for quick checks, it's really, really useful. but unless you've got somebody with some FEA experience, it really takes. I did it for a year at Pratt and Whitney, and even by the end of that, I was by no means an expert in FEA. Um, it takes a lot of experience to be able to properly set up a finite element model. And I mean, I've spent weeks on models before full time. Uh, it's not something that's really practical. Most cases in FRC. Um, we approximate a lot of things. We, instead of doing fatigue calculations a lot of the time, we'll just look, are we under half yield? Okay, good, ship it. Next thing. Because there's so many things you got to get through, that if you're spending more than, I think if you're spending more than like 20 minutes on FEA for a part, you're wasting your time.
That makes sense. All right, thank you, Bobby. That
All right.
was incredible. If people want to go over your workshop and your presentation, we'll hopefully publish that on our website and then Chief Delphi after the event. But thank you so much, Bobby.